In this lecture, we're going to discuss the divergence and the curl of electric field. In the last lecture, we discussed about Helmholtz theorem for the electric field. We saw that if we know the perpendicular component of the field, and if we know the divergence, and if we know the curl, then we can determine the field everywhere else due to any charge distribution. First, we're going to focus on the divergence of the electric field. So in order to understand the divergence of the electric field, we're going to see what is the divergence of a fluid flow. Imagine you have a box which has dimension A, B and C, and it has faces 5, 6, 7, 8 and 1, 2, 3, 4. And there is a fluid flowing through this box, and we would like to know what is the divergence of this fluid and also how to write this in mathematics. So first, let's consider the phase 5, 6, 7, 8 and what is the fluid leaving this phase. So in order to know what is the fluid that is leaving this phase, we would like to know what is the velocity of the fluid on this phase 5, 6, 7, 8. And then what is the area of this box. So the velocity is v, and we take the x component and then we multiply by the area. Now since we see that the fluid is entering through the phase 5, 6, 7, 8, so the velocity is going to be negative, and then we multiply by the area. Now let's see what is the fluid that is leaving the phase 1, 2, 3, 4. In this case, we have a velocity and then we multiply by this x hat at x plus a, y and z, and we also multiply by the area. In this case, the velocity is positive because the fluid is actually leaving the phase 1, 2, 3, 4. Now this thing is equal to Vx times the area plus del by del x Vx a. So this thing is change in velocity with respect to x, and what is the total velocity that changed in the distance a. So this whole thing gives us the change in velocity of the fluid when the fluid is traveling the distance a, and then we multiply by the area. Now let's see what is the net flow through the surface perpendicular to the x-axis. So basically what we have to do is to add the flow from the phase 5, 6, 7, 8 and the flow from 1, 2, 3, 4. The flow from the phase 1 is this, and the flow from phase 2 is this, as we have seen in the last slide. So we can see that this part cancels out with this part completely, and we are left with only this part, which is this. Now this is only in the x direction. We can also calculate similarly the flow through the box in y and z direction, which is nothing but del by del x Vx into a into the area, del Vy upon del y into b into the AC. In this case, we are seeing the change in velocity in the y direction, then we are multiplying by b because we want to calculate what is the change in velocity when the fluid is traveling the distance b, and the area is a times c in this case because this is perpendicular to y. In this case, we have del Vz upon del z into c into a times b. So this is the velocity change of the fluid when the fluid is traveling the distance c in z direction. Now we can see very easily that we can take a, b and c common, a dot b dot c, and we left behind del Vx over del x plus del Vy over del y plus del Vz over del z. This is just the divergence of a vector that we can write here, and this ABC is just delta V. Now let's talk about the divergence theorem. So in this case, we have a similar box which has a dimension A, B and C. This time we're going to consider the area vector. So in order to calculate fluid flowing through this surface, number 1 is minus V times the area vector. The area is B times C, so B times C in the x direction. The direction of area is always perpendicular to the area. Then the fluid that is leaving the phase 2 is V times the area vector. Here the area is same, BC. The vector is this one, x plus a, y, z. So essentially what we are doing is doing a dot product of velocity vector with the area vector here as well. So we can add all of this dot product v dot ds. Then we can get the fluid that is flowing through the box. Then we can take the integration limit and we can get this value, the integration v dot ds. Now we have seen in the last slide that the fluid that is leaving the box is equal to this, and here we saw that it's also equal to this. So we can equate both of the equations. Now let's imagine you have a volume which has a random shape. In this case, we will consider a small area on the surface, and then we're gonna calculate the surface integral over v dot ds, which is equal to del dot v into delta v. And this way we can write the divergence theorem. Now let's see what is the divergence of electric field, because we have seen the divergence of a random fluid with a velocity v. So from the calculus we know that the divergence of any field is del over del x ex, del over del y ey, plus del over del z ez, which is equal to del dot v, the divergence of any vector. Similar to the fluid case, we can also take the area here, and we can see that E dot ds for the electric field is also equal to del V into the divergence of electric field. This way we can write the divergence theorem for the electric field, which is del dot E into dV and then integration, which is equal to E dot ds and the surface integration. So we already have seen the divergence theorem. So let's talk about the curl of the electric field. So the curl of the electric field is del cross E, which is equal to del Ez over del Y minus del Ey over del Z in the x direction. And then you have the Y component, which depends on the x component of the electric field and the Z component of the electric field. And then you have a Z component of the curl, which depends only on the Y component of the electric field and X component of the electric field and how they are changing. So this is the change in the Y component when you are moving in X direction, and then this is the change in Ex when you are changing in the Y direction, which is obviously equal to del cross E. This is the del operator, and then you have the electric field vector. We can also write this in form of a determinant, where we have the unit vectors for the directions, and then we have an electric field vector, and then we have the components of the operator. So now let's see what does it mean, what curl actually means and what it is about. Just imagine you have an electric field which is circulating around, and then you have a distance dl on this circle. Then we want to calculate E dot dl for all of the small lengths, all of these dl's, and you add all of these dl together, and we're gonna get E dot dl for whole circle. So we're gonna take a very simple case, just like the divergence. So we have an area which has coordinates x comma y, x plus dx comma y, x plus dx comma y plus dy, and then x comma y plus dy. And then we have three paths in this box, 1, 2, 3 and 4. So what we want to know is to calculate E dot dl for the path number 1. So in path number 1 we have the electric field Ex, x comma y, and then we are traveling distance delta x in this path. In the path 2, you have Ey because we are traveling in the y direction, so we need Ey, and then we multiply or we do the dot product with the dl, which is delta y. This Ey is nothing but Ey at x comma y, and then how much Ey changed when we moved in x, and then we multiply by the distance that we moved. So here In the path 2, we moved delta x distance, so we multiply by delta x. And then this whole thing is multiplied by dl, which is delta y in path 2. In the path 3, we have ex, x plus dx, and y plus dy. And then we multiply by the distance, which is delta x here. And this value, ex, is nothing but ex at x comma y. Obviously, we have negative sign because we are moving in the opposite x direction. And then the change in ex when you are moving in y direction. And then you multiply by dy. And then we multiply by delta x, which is the length, or which is the distance that we traveled here in the path 3. Similarly, we can calculate the E dot dl for path 4, which is ey x comma y plus dy dot product with dy. This is equal to ey at x comma y, and obviously there is a negative sign because we are going in minus y direction, and then we multiply by the distance, which is delta y. Now let's add all of these together. So this is the E dot dl from path number 1, and then you have E dot dl from path number 2, which is this one, and then you have E dot dl from path number 3, then you have E dot dl from path number 4. What we see here is that this term cancels completely with this term, and then this term completely cancels out this one. So we are only left with these two terms, this one and then this one. So we can add these two terms together and we get this one. So del ey del x into del x del y minus del ex over del y into delta y and del x. Now we can take del x del y outside and we left with del ey over del x minus del ex over del y, which is nothing but the z component of del cross E, the curl of electric field. So the whole E dot dl that we calculated for these paths is equal to del cross E, the z component of del cross E in the z direction, and then the area vector, which is del x del y in the z direction as well. Similarly, we can also calculate E dot dl for the boxes which lie in other planes, and we're gonna get the x and y component of the curl as well. So now, since we understood how to calculate the curl of electric field, let's see what happens in a shape which is more or less random. So we're gonna divide this shape into small boxes, and we're gonna consider only two of them, and we're gonna calculate E dot dl for these two boxes. What we see is that the connecting line, this one, will be cancelled out because when you are considering this box, you go this way, and then you are considering this box, you are going this way. So this line is calculated twice, which is going to be equal to each other but in opposite direction. So E dot dl is going to be 0. So essentially in these two boxes, what we are getting is the E dot dl of the outer boundary. So essentially what we can do is to calculate the E dot dl for all of the small rectangles, and then we add all of the rectangles, and what we're gonna get is the E dot dl from the whole boundary here, this boundary, which is equal to the surface integral of E dot dl. We saw in the last slide that E dot dl is also equal to del cross E dot area vector from each rectangle, and then you add all of the rectangles. Now we can equate these two values, and we see that del cross E dot ds is equal to the surface integration E dot dl. This is nothing but the Stokes theorem. So in this video we have seen the divergence theorem, and then we also saw Stokes theorem. To remember it, what we can do is to see that the divergence theorem goes from delta V, is the volume which is in 3D, to ds, which is in 2D. The Stokes theorem goes from 2D, a surface area, to 1D, which is dl.